Section 10.3 is on arcs and chords. And in this section, we're going to have a whole bunch of theorems, and then I'll do several examples at the end. The first theorem says that two minor arcs are congruent if and only if their corresponding chords are congruent. So for example, if chord AB is congruent to chord CD, then arc AB is congruent to arc CD. Notice that chord AB cuts off this minor arc AB, and chord CD cuts off this minor arc CD. So if AB is congruent to CD, then arc AB is congruent to arc CD. And conversely, if the arcs are congruent to each other, then the chords are congruent to each other. Let's do a quick example here. So it's given that arc RS is congruent to arc TV, and we need to find the length of RS, and we're given that the length of the RS is 7x minus 2, and TV is 5x plus 6. Well, if arc RS is congruent to arc TV, then chord RS is equal to chord TV, or 7x minus 2 is equal to 5x plus 6, or 2x is equal to 8, or x equals 4. Notice we're not done. We need to find the length of RS. RS is 7 times x minus 2, or 28 minus 2. RS is 26. So if two arcs are congruent, their chords are congruent, or if two chords are congruent, then their arcs are congruent. Here's another theorem. If a diameter or a radius of a circle is perpendicular to a chord, then it bisects the chord and its arc. So for example, if AB, which is a diameter, is perpendicular to XY, which is a chord, and it is indeed perpendicular because I have the little right angle symbol in there, then XZ is congruent to ZY, and arc XB is congruent to arc BY. Because this diameter and this chord are perpendicular, the chord is cut in half exactly, and the arc out here is cut in half as well. Here's another theorem. If a segment is a perpendicular bisector of a chord, then the segment is a radius or a diameter. So it's sort of like the converse of the previous one. So if I have a segment in a circle that is a perpendicular bisector of a chord, okay, so I have chord XY here, and if AB is perpendicular to it, then AB is a diameter. Here's another theorem. Two chords are congruent if and only if they're equidistant from the center. So here we have chord FG, and here we have chord JH, okay? And if they are congruent to each other, then they are the same distance from the center, which means LX is equal to congruent to LY. Now remember, when we're talking about distance, we're talking about perpendicular distance. So to determine how far FG is from the center of the circle L here, I would have to draw a line perpendicular from L going to FG, and then the same thing over here to determine the distance from chord JH to the center L. I would have to draw this segment here, LY, which is perpendicular to JH. So if FG is congruent to JH, then LX is congruent to LY, and conversely, if LX is congruent to LY, then FG is congruent to JH. Okay, let's take a look at several examples here. I got these right out of the textbook. So for these three, we need to find the value of X. And in diagram number 1 here, we have a circle with two congruent chords. Chord RS is congruent to chord ST. And I know because angle S, whatever the center is, T, this angle here is 93 degrees, I know that this arc right here, I'll go ahead and draw it on there, I know that this arc is 93 degrees as well. And since ST is congruent to RS, it's going to be congruent to this arc as well. So the measure of X is going to be 93. If the chords are congruent, then the arcs are congruent. Example number 2 here. I have two congruent chords, FG and GH, and I know they're congruent because they tell me the measure of 4. And I have arc FH is 220 degrees, arc GH is X, but I also know that because these chords are congruent, GH is going to be congruent to GF, so I know that the measure of this arc is also going to be X degrees. And I know that all of the arcs of a circle add up to 360, so I have 220 plus X equals 360, or 2X is equal to, subtracting that, 140, or X is equal to 70. I'll go ahead and box those. Okay, and my third example here, I have arc AB, which measures 127 degrees, and arc CD, which also measures 127 degrees. Since these two arcs are congruent to each other, then their chords are also going to be congruent to each other. So I have 5x is equal to 3x plus 6, or 2x equals 6, or x equals 3. Here's two more examples. So we have circle P, and the length of JK is 10 units, and the measure of arc JLK is 134. We need to find each measure and round to the nearest hundredth. But looking at this picture, chord JK is perpendicular to diameter ML, so I know that JK is bisected or cut in half. All of JK is 10, so I know that JQ is 5 and QK is also 5. I also know that since arc JLK measures 134, that each of these smaller arcs is going to measure half of that, or 67 degrees. So looking at number 4 here, the measure of arc JL is going to be 1/2 of 134, and we already did that and came up with 67 degrees. Now I need to find the length of PQ, and this one's a little more difficult. So I know that the radius is 6, from M to P is 6, so that means from P to L is also 6, but I can't just assume that JK cuts that in half. I can't just assume that this is 3 right here. And there's a little bit of a trick to doing this one. What you have to do is you need to draw a radius, and I'm going to erase that and I'll put it back later. You need to draw a radius from P to K. That's a little wobbly. So draw radius PK. Okay, now I know a couple things about this. As I said before, KQ was 5. PK, because it's a radius and all radii in a circle are congruent, its length is 6 units because MP is a radius as well. Now do you notice what we have? We have a right triangle here, PQK. I know one leg of the right triangle. I know the hypotenuse of the right triangle, and what I'm trying to find right here is PQ, which I will label as X. So from here I can use the Pythagorean theorem. I can say x squared plus 5 squared equals 6 squared. Or x squared is equal to 25, or x squared plus 25 equals 36. X squared equals 11. So x equals the square root of 11, which is approximately 3.37. Okay, so the trick to doing a problem like this is to draw a radius, and you can go ahead and do that because P is the center and K is a point on the circle, and then use the Pythagorean theorem. And our last example here gives us circle J, and in this circle we know that GH is 9 and KL is 4x plus 1, and we need to find x. Well, notice chord GH is 5 units from the center J, as is chord KL. It is also 5 units from the center J. Remember the theorem that said that if two chords are equidistant from the center, then they're congruent to each other. So GH is equal to KL, plugging in the values that were given, and solving for x, we get that x equals 2. Okay, so lots of theorems in this section. Make sure you're familiar with them and that you know how to apply them to the different